Hi everyone. As part of our next video in the detection series, we are getting into YOLO v5. Since there isn't an official paper for this one, the contents of this video are mostly derived from the official implementation, which is provided by Ultralytics. The three main components that this video would cover is the architecture of YOLO v5, where we will see what changed from YOLO v4, how do we assign targets to anchor boxes and grid cell pairs in YOLO v5, and third would be the loss, which looks similar to other previous versions but has some minor changes. We will also touch upon augmentations, AutoAnchor feature of YOLO v5, and some other small details along the way. This video will refer to a lot of components that I have already covered in YOLO v4 video, like CSP residual blocks, PANet, complete IOU, and so on. All these are also present in YOLO v5. But for this one, I will assume that you are already aware of these. If that's not the case, then you could either watch my entire YOLO v4 video first, or simply refer to the relevant sections of that video as and when needed. Let's start with the architecture. Since most of the layers used in YOLO v5 are same as v4, first let's revisit YOLO v4 architecture. The backbone of v4 was a series of convolution layers and CSP residual blocks. CSP residual blocks divided the input in two parts. One part goes through n residual blocks, where n is different for different stages of network. The output of these residual blocks goes through a convolution layer and then is concatenated with the other part of CSP input. After feeding this concatenated feature map to a 1x1 conv layer, we have the output of a CSP residual block. After all the conv layers and CSP blocks, our output, which is of size 1/32 times the original image, is passed again through few convolution layers and then through a spatial pyramid pooling block. Inside SPP, the input is concatenated with max pooling outputs of different kernel sizes. And the purpose of this SPP block was to increase the receptive field of backbone features. With SPP, we come to the end of backbone of YOLO v4 and move to our neck. Similar to path aggregation network, neck of YOLO v4 has a top-down pathway and bottom-up pathway. In top-down, we have convolution layers, followed by upsampling, and after every upsampling, we concatenate with similar resolution feature from the backbone layers. Then we have the bottom-up pathway, where now we move from size by 8 to size by 32 features, and this time downsample features. After every downsampling, we concat with similar resolution feature from the top-down pathway. Head of YOLO v4 uses features of different resolutions from the bottom-up pathway to make predictions for different scale of anchor boxes using 1x1 convolution layers. Now we'll make some changes in this YOLO v4 architecture to get to YOLO v5. The first change is that the input goes through a 6x6 conv layer with stride 2, batch norm, and sigmoid linear unit as the activation function. In fact, in YOLO v5, all convolution layers will have the same activation function. So the downsampling layers will also be 3x3 conv with sigmoid linear unit activation. Since the first 6x6 and next 3x3 conv layer will end up reducing the size of feature to image size by 4, YOLO v5 has 4 CSP residual blocks. This is for the case when the stride factor of network is 32. In some variants, we also work with stride factor of 64, and in those, we have additional CSP residual blocks. There is also a change in the n values for each block. Like we saw for YOLO v4, these n values are the number of residual blocks that one part goes through. The partitioning is again done via 1x1 convolution layers, with each part having half channels. After one part is fed through n residual blocks, we concatenate, and using a 1x1 convolution layer, we get the output of CSP residual blocks of YOLO v5. So in terms of CSP blocks, apart from the activation change, YOLO v5 also gets rid of the 1x1 conv layer, which was present right after n residual blocks prior to concatenation. The last part of backbone is spatial pyramid pooling fast block. This has the same responsibility as SPP of YOLO v4, that was increasing the receptive field of backbone. However, the difference from YOLO v4 is that instead of each max pooling layer working on the original input, we now have 3 max pooling layers, each with same kernel size 5, one after another. So each max pooling layer working on the output of previous one. This has the same effect as SPP of YOLO v4 but ends up being faster to compute. In the repo, the authors mention that SPPF is about 1 by 3 times faster than SPP. These max pooling outputs are concatenated with original input after it's fed to a 1x1 conv layer, and this concatenated feature map again goes through a convolution to give us our SPPF output, which is also the output of backbone. The neck is again very similar to YOLO v4 with top-down and bottom-up pathways, but in YOLO v5 we have CSP blocks in both the paths. We have our top-down pathway taking x by 32 sized features to x by 8, and for this the SPPF output first goes through a 1x1 conv layer, and then after upsampling we concatenate with x by 16 sized features from the backbone layers. Then we have a CSP block. Note that these are not residual blocks. So like backbone CSP blocks, partitioning happens, but we don't have residual connections, just a series of 1x1 and 3x3 layers. We again have this sequence of upsampling, concatenation, and CSP block. And from this x by 8 sized features, we now move to our bottom-up pathway. Bottom-up pathway will be a sequence of downsampling, concatenation with same sized feature from top down, and then CSP block. This bottom-up pathway ultimately takes us to our x by 32 sized features. From the 3 different resolution features of bottom-up pathway, we predict transformations for anchor boxes of different scales. And this is done using 1x1 convolution layers, just like YOLO v3 and v4. What we have now is YOLO v5. These being the backbone layers of YOLO v5, this whole part is neck, and head remains exactly same as YOLO v3 and v4. Next, we'll look at how predictions are made in YOLO v5. In YOLO v3, feature maps of different resolutions are used to predict transformations from a predefined set of anchor boxes. Each feature level is associated with different scale of boxes at each feature map location. So a prediction for an image from one of these levels will have box predictions for each feature map location at that level, and for each location we make predictions for all anchor boxes. These box predictions were made by predicting 5 plus c values. 4 of them were transformation parameter predictions, which led us to compute the coordinates of box. One of those values corresponds to objectness prediction, which indicated how likely this predicted box contains an object, and the final C values were the class conditional probabilities for all classes. All these aspects are also present in YOLO v5, but things change a bit when we come to how the transformation parameters are defined. We know that YOLO v3 predicts the center of the box by having the network learn to predict offsets tx and ty from the top left corner of the grid cell. And tw and th were the width and height transformation parameters, defined as log of target width and height by anchor width and height. These transformations enabled us to compute the exact box coordinates. In YOLO v4 video, in the section on grid sensitivity, we saw how the authors used a modified XY prediction computation with this expression. The reason was that earlier, the network would have a tough time to predict box centers on boundaries of grid cells, as the sigmoid output would predict 0 or 1 only when the argument would have a very high absolute value. But using this expression, we have reduced the extent of that problem, as now the range of offset values that can be predicted by the network are larger than 0 to 1. So for predicting box centers on grid cell boundaries, we don't need the sigmoid output to be 0 or 1. YOLO v5 has the same expression for XY coordinate prediction with a value of 2 used for alpha. The main change happens in the width and height transformation parameters. In YOLO v5, unlike the previous versions, the width and height transformation predictions are no longer unbounded and also use sigmoid activation. Width and height of predicted box is defined as anchor width and height times 2 times sigmoid of TW or TH square. Since the sigmoid output will always be 0 to 1, this means an anchor can be transformed anywhere from 0 times its width and height to 4 times its width and height. Now for training a detection model that generates these prediction boxes, we need to match these predictions to either some foreground target box or background. The matching strategy that we have seen in previous versions of YOLO was to use the grid cell that contains the center of ground truth. Then out of all the anchor boxes, we pick the one that has maximum IOU with the ground truth and match this grid cell anchor box pair to the target ground truth box. Unmatched grid cell anchor box pairs are treated as background. YOLO v5 deviates from this approach. Given an anchor box and ground truth, YOLO v5 first computes if this anchor box can be matched to this ground truth or not. This is done by computing the ratios of ground truth dimensions with anchor box dimensions. An anchor will only be matched to a ground truth box if this ratio is between 1 by anchor t and anchor t, where anchor t is a threshold which acts as a hyperparameter for YOLO v5. The default value of this anchor t is 4, which means an anchor box can only be matched to a ground truth box if its dimensions are greater than 1 by 4 times and less than 4 times the ground truth dimensions. This matching criteria has few implications. Since we are no longer using IOU for deciding which anchor to match to which target, this means if an anchor can be modified to match the ground truth box given the constraints, then it's matched to a target even if it's not overlapping with the target at all. Second, multiple anchors can be matched to the same ground truth box, as long as both their dimensions match the constraint. Third, and this one is interesting, multiple ground truth boxes can also be matched to the same anchor box. And last implication is from using the lower threshold of 1 by 4. Since the anchor box can only be transformed anywhere from 0 to 4 times its width and height, the presence of upper bound of 4 makes sense. But the lower bound of 1 by 4 ensures that small ground truth boxes are more likely to be matched to small scale anchor boxes of higher resolution feature map. This is good for us. As for smaller ground truth boxes, we are better off with smaller anchor boxes and using higher resolution fine-grained features, rather than having large-scale anchor boxes matched to these very small targets. So for matching anchor boxes, we use the height and width ratio. Now what about grid cells? Up till now, the approach is that we look at which grid cell contains the center of target box, and that grid cell becomes responsible for predicting this target. The model then learns to predict offset of ground truth center from top left corner of this grid cell. In YOLO v5, we do that, but additionally also include adjacent grid cells and make them also responsible for predicting that ground truth box. But why? And more importantly, how would we do that? Well, for this ground truth box, the grid cell containing the center would be this one. However, because of the modified offset expression, which has now changed the range of possible offset values to be from minus 0.5 to 1.5, because of this, even the center cell can be made responsible, since the offset from top left corner of center cell is less than 1.5 in both directions. In YOLO v5, we use this to have more cells responsible for predicting a ground truth target. For every grid cell containing the center of target box, we also include any of the 4 adjacent cells, if we can. The key part in that line being if we can. Like if the center is here, other than this grid cell, which contains the center, we only have to consider 2 possible adjacent cells. Furthermore, if the center is here, only these 2 possible adjacent cells can be included, because for the other 2, the ground truth center is outside the range of possible values of offset that our model can predict. To handle both these cases, given a target center, we divide the main grid cell, that is the cell that contains the center, into 4 parts. If the target center is in the top left part of the cell, then these grid cells are all responsible. If it's on the top right, then these 3. Bottom right will lead to these cells being responsible, and for the last bottom left corner, we end up with these responsible grid cells. Also, cells on left or right can only be included if there is indeed a cell in that direction, and same for top and bottom. Now let's go back to our example target box in the image and summarize the steps for matching target boxes to anchor and grid cell pairs. We first get all the anchor boxes and find which of them matches the constraint of height and width ratio with this target box. Suppose these two are matching our ratio criteria. Then we get the grid cell containing the target center, and depending on the center location, include additional adjacent grid cells. Which means in this example, these 3 grid cells and these 2 anchors for each of these 3 cells would be responsible for predicting this target box. We will also go through the YOLO v5 repo implementation to understand how all of this that we talked about looks in code. And for that, we are just interested in this build targets function in compute loss class. This method will match ground truth boxes to anchor box grid cell pairs. Let's go through it line by line. The method receives the prediction and targets as the arguments. Prediction would be a list with each element being the predictions for a layer. So each element of this would be of shape batch size, cross number of anchors, cross grid dimension, cross 5 plus number of classes. The last dimension will be our tx, ty, tw, th predictions, objectness score predictions, and class conditional score predictions. Targets would be n cross 6, where n is the aggregated number of targets in all the current batch images. The 6 elements in the second dimension correspond to batch index, ground truth class index, and box coordinates in XYWH format, normalized from 0 to 1. Let's work with a specific case of batch size being 1, number of targets in that single image to be 2, and number of anchors to be 3. This gain will be used to convert image coordinates to grid space coordinates. So later we'll multiply the target box coordinates with these gain values. But as of now, they're all just 1. Now even though target is n cross 6, we have gain to be a 7 element tensor. And that's because soon we'll convert targets to have 7 values in the last dimension. In this line, we are creating anchor indexes tensor, which is of shape number of anchors cross number of targets. In our example, this AI would be 3 cross 2, and the values will just be the indexes for the anchors repeated as many times as there are ground truth targets in the batch. This is needed because we'll be computing that matching ratio between each anchor and ground truth pair. Now we are going to convert targets from n cross 6 to number of anchors cross number of targets cross 7. So here we are creating anchor target pairs together with target values. So for our case, this will be 3 cross 2 cross 6. And then to the values of last dimension, which is the 6 target values for a ground truth box, to that we are going to be appending the anchor indexes. So as of now, we have 3 times 2, 6 anchor target pairs. This here is just defining the offset values for each of the 5 grid cells, center, and 4 adjacent cells. We could also include 8 adjacent cells, but the repo only works with these 4. Then we loop over predictions from each of the layers. Inside the loop, we get the anchors for this layer and use the predictions for this layer to get the number of grid cells in X and Y direction. This will allow us to update the gain so that when we later multiply target coordinates with gain, we will essentially convert image space coordinates to grid space coordinates. That happens here. And this makes T to be of same shape as targets, which is 3 cross 2 cross 7. Now we find which anchor ground truth pairs have valid height width ratio. So J will be a Boolean value for all 6 anchor ground truth pairs. We will then filter out those pairs which do not meet the ratio constraint. In this example, let's say that's 2, which means only 4 out of 6 anchor target pairs have valid ratio between 1 by 4 and 4. For these valid pairs, we get their xy coordinates in grid space, and we also capture how much grid space is left on the right and bottom of the target center. Then this line here gives us j and k, which are Boolean values for all selected anchor target pairs. J tells us whether the left cell needs to be included or not, and k tells us whether the top cell needs to be included or not. The first dimension of gxy mod 1 gives us the decimal part of x coordinate of the center in grid space. If this is less than 0.5 and if gxy0 is greater than 1, this means that there is a valid left cell that needs to be included. So j would be true in those cases. Similarly, the second dimension of gxy mod 1 gives us the decimal part of the y coordinate of the center. If this is less than 0.5 and if gxy1 is greater than 1, this means that there is a valid top cell that needs to be included, which is this Boolean k. L and M are similar tensors, but for right and bottom cells. You can see that the first dimension of gxi mod 1 gives us the decimal part of the region on the right of center in grid space. And if this is less than 0.5 and if gxi0 is greater than 1, this means that there is a valid right cell that needs to be included, which is the Boolean L. These 4 masks tell us about adjacent cells, but we'll also need a mask for the cell that contains the center, which should always be true. So by stacking an all-one tensor and jklm, we get J, which is now 5 cross 4 tensor, having Boolean values for all 5 possible cell locations for all 4 valid anchor target pairs. Now each of the valid anchor target pairs gets repeated 5 times to give us 5 cross 4 cross 7 tensor. So basically 20 grid cell anchor target combinations. From these we select those grid cell and anchor target combinations that are valid. In this example, let's say these 12 valid combinations exist, meaning we have T as 12 cross 7. From our offsets that we had defined earlier for 5 cells, we first create offsets for all cell anchor target combinations. This offset variable will be used to compute the correct target offset for all the cells, which happens in this line here. From target xy, which is 12 cross 2, we subtract the offsets to get the ij values of responsible grid cell. As of now, we have matched targets with anchors and grid cell pairs. And once the matching is done, we'll simply aggregate all information required to compute the loss. These index values are the batch index, anchor index, and grid cell ij values. And these are for all the foreground grid cell anchor box pairs in the batch. We then save the target box offset parameters for all these, which will be gxy minus grid cell ij values, and also save the width and height values in grid cell space. This method repeats this computation for all layers and returns the ground truth classes XY parameters for target box and its width and height, all the index values that we saved, and anchors for all the valid grid cell anchor target combinations for all layers. And when I say valid, I mean these are supposed to make predictions for an object. While computing loss, we will use these index values to select foreground grid cell anchor combinations. Remaining all combinations, for example this grid cell and all its anchor boxes, will have target as background. Now that we have matched targets to anchors and grid cell pairs, it's time to look at loss. YOLOv5 loss is similar to what we have been seeing in past few detection videos, where loss is a combination of bounding box or localization loss, classification loss, and objectness loss. Here in YOLOv5 also, it's the same. But localization loss is complete IOU loss between predicted and target boxes, where predicted box's xy coordinate offset is 2 times the sigmoid of tx and ty prediction, minus 0.5. And then we add grid cell locations to it. Width and height of predicted boxes are square of sigmoid of tw and th times 2 multiplied with anchor width and height. Classification loss is binary cross entropy with ground truth class target as 1 and rest as 0. Objectness loss is also BCE, but for foreground boxes, the target of objectness loss is the complete IOU between predicted and target box. And of course it's 0 for background boxes. Since all these losses will be coming from predictions from multiple layers, so if we have 3 layers, then we will have 3 localization, classification, and objectness losses. The total localization and classification loss is just sum of these individual losses. But in YOLOv5, total objectness loss is weighted sum of objectness loss from all layers, with typically the loss coming from highest resolution feature map having the highest weight. Total loss is then the weighted sum of these 3 losses with different weights. In YOLOv5 repo, this loss is ultimately also scaled with the batch size. Let's again look at the code for this in YOLOv5 repo. For this also, we are going back to the compute loss class, but this time we'll look at the initialization and forward method. We first initialize our classification and objectness loss. This line is for label smoothing, which by default is not used in YOLOv5. Focal loss again is not used by default. Then we have balance parameter. So these are the weights of objectness loss coming from different layers. If we are using predictions from 3 layers, then the weight values will be 4, 1 and 0.4 from the highest resolution to lowest resolution features. There are versions of YOLO which has 4 or 5 different prediction layers, so the other list of values are weights for that case. SSI is the index of stride 16 layer, and we can ignore this as this is only used when auto balance is set to true. Basically, when auto balance will be true, then we'll also update these balance weights. In the default case, the weights are fixed and SSI will not even be used. Moving to the forward method, same prediction and targets are passed as arguments. Then we call our build target method, and that will give us the index values for valid grid cell anchor box pairs and their assigned target boxes and target classes. Now we are going to compute losses for each layer. We first get the valid foreground batch, anchor, and grid cell indexes. Then initialize objectness target as 0 for all the predictions. After that, get the predicted transformation parameters as well as class conditional probabilities. We use the transformation parameters to get predicted boxes and then use complete IOU to get overlap between predicted and target boxes. Localization loss for each layer would just be the mean complete IOU loss. Then we are going to set objectness target for the foreground grid cell anchor combinations. Now if you remember during matching logic, each anchor can be matched to multiple ground truth. This part of code ensures that the objectness target for each foreground grid cell anchor box combination is the complete IOU value between the predicted box and the ground truth target with which that predicted box has highest overlap amongst all the ground truth that is matched to this grid cell anchor box pair. We set the objectness target for the positive anchor grid cell pairs with these IOU values. Next part is classification loss. If label smoothing is not enabled, then this is just setting 0 for all classification targets and then setting 1 for the ground truth class index for each grid cell anchor box pair. This line computes objectness loss and then scales it for each layer based on the balance parameter value for that layer. If auto balance is enabled, we also update the balance weights depending on the objectness loss values and further scale the weight values using 1 by stride 16 layers weight. But since auto balance by default is disabled, which means the layer weights won't be updated at all. With all three losses computed, we multiply these with their respective weights and then using the batch size scale the summation of these three losses. And that becomes the total YOLOv5 loss. With architecture, matching strategy and loss covered, we have now gone through all the core parts of YOLOv5. In this video, for the remaining part, I'll talk about augmentations in YOLOv5, its AutoAnchor utility, and then go through results on Coco dataset. Let's start with augmentations. And these are taken from the hyperparameter file for Coco dataset. YOLOv5 uses the same augmentations more or less that we have covered so far. The two new ones are copy-paste and mix-up. In copy-paste, we copy segments and their labels from an image and paste them onto a different image to generate a new training sample. Mix-up creates new samples by linearly combining two random images of the dataset. Their labels are also linearly combined. Mosaic I've already covered in YOLOv4, where 4 or even 9 images are combined, making a grid of images, and this enables the model to be better at detecting objects at different scales and in different contexts. These two are left-right and up-down flip augmentations. Then we have a bunch of affine transformations and perspective transformation, as well as HSV augmentation. Apart from these, YOLOv5 also uses augmentations from Augmentation library. The specific values for these augmentations, as well as other hyperparameters, are reached by starting with an estimate and then using genetic evolution algorithm to evolve those hyperparameters. The algorithm runs over a large number of generations, where at each step, we get a fitness score of the current parameter choices. For example, MAP could be a metric for fitness score, and then keep on mutating the parameter choices using a predefined mutation probability and variance value for each parameter. Mutation probability decides how often that parameter should be modified, and variance dictates how much it should be modified. From augmentations, let's move to AutoAnchor. YOLOv5, prior to training, checks if the anchors provided are decent choices for the dataset, and if not, then again uses genetic evolution algorithm to evolve the anchor choices to better fit the dataset. Let's just go through this AutoAnchor file as well. The main method is check_anchors, which first gets the different dimensions of target boxes present in our dataset. We randomly modify scale of those target boxes to create a list of width and height dimensions representing objects of our dataset. Then we define this metric function, which generates a score of how well the anchors fit the dataset. It basically computes the height and width ratio between anchor boxes and target boxes. The two metric it computes are anchors above threshold, which is for a target box, on average, how many anchors match our ratio criteria. Second is best possible recall, which is for how many ground truth targets the best anchor has height and width ratio between the thresholds. Then if best possible recall is greater than 0.98, we are good to go. If not, then in YOLO v5, we call this method. In this, we first run k-means to start off with a decent set of anchor choices, and then use genetic evolution algorithm to evolve these k-means returned anchor choices over 1000 generations. The fitness score used for these evolutions is again using the same ratio metric between current anchor choices and target boxes of our dataset, and converts that into a score. The creators of YOLO v5 provide multiple versions of the model, catering to folks that require higher detection speed, so a very light version called Nano, as well as to ones that require high accuracy, which is their extra large model. Let's look at the configurations of their large model, which is YOLO v5L, and then later we'll see how this configuration changes from lighter to larger versions. In the config, we have our number of classes and depth and height multiplier. This depth and height multiplier we'll talk about later. Then we have the anchors. So these are the width and height of anchors at all the different levels. According to this config, predictions are made from feature maps of 3 different levels. After that, we have the backbone configuration, which has config for each layer, and the format is that the first value refers to which layer's output will this layer use. -1 just means the previous layer. Second value refers to the number of repeats for this layer. For CSP layers, this will refer to the number of residual blocks. Third is the module name for the layer, and fourth value are the arguments for that module. So for convolution layers, it would be channels in output, kernel, stride, and padding. As we had seen in architecture section, YOLO v5 also has CSP residual blocks, which is this layer. So here the 3 refers to n, which was how many residual blocks does this CSP block have. The last layer of backbone is spatial pyramid fast pooling module. After backbone, we have the configurations for head, which has this top-down bottom-up structure. And finally, we have our detect layer, which makes predictions from the 3 different sized feature maps of bottom-up pathway. The key difference between different YOLO v5 version configurations are these two, depth and width multiplier. For YOLO v5L, this is 1 for both. For YOLO v5S, this would be 0.33 and 0.5. And for extra large version, this would be 1.33 and 1.25. Width multiplier controls the number of channels that each layer is going to use. For example, the configuration of all YOLO v5 versions have 1024 as the channels in the SPPF module. But when width multiplier is 1.25 for YOLO v5X, this means for extra large model, SPPF will be using 1024 times 1.25, which is 1280 channels. For YOLO v5S, with the width multiplier being 0.5, that means SPPF will generate output that will just have 512 channels. Depth multiplier controls the number argument for each layer. So default value of first CSP layer is 3. But when depth multiplier is 1.33, that means 4 residual blocks will be used in the CSP layer. This way, the depth and width multiplier controls the sizes of all the different YOLO v5 versions. Apart from these 5 variants of YOLO v5, there is also a YOLO v5 P6 version, where the backbone has a stride factor of 64 with 5 CSP residual blocks, and also a P7 version, where the backbone has a stride factor of 128 with 6 CSP residual blocks. For the P6 versions, predictions are made from 4 feature maps, from sizes size by 8 till size by 64, whereas for P7, predictions are made from feature maps of size by 8 till size by 128. The repo also has versions which cater to other tasks, like instance segmentation. In the last part of this video, we'll look at results for YOLO v5, but we will only focus on the 5 variants and their corresponding P6 version. When evaluated on COCO dataset, YOLOv5X, the largest variant, achieves an AP of 50.7 with an image size of 640 x 640. In terms of inference time, it takes about 12 milliseconds. Obviously, moving to smaller variants, that is from extra large all the way till nano, we get higher speed, but also lesser accuracy. With YOLOv5N, accuracy drops to 28, but speed is close to about 150 FPS. Using the P6 versions, the accuracy increases, but again we also see a decrease in speed. And comparing YOLOv5 to V3, V4 and other detectors, one can see that YOLOv5 fares very well in comparison to them. The YOLOv5 version transitioned from darknet framework, which YOLOv4 used, to PyTorch. However, as of today, we also have PyTorch implementation of YOLOv4. But apart from framework change, there were quite a few different aspects introduced through YOLOv5. So do check out the repo and try to go through the implementation by yourself. And for folks who are trying to understand YOLOv5 or even trying to implement YOLOv5, hopefully this video will assist you in that process.